Now, if you're watching online, you'll notice that probably know that if you've ever watched any of my videos before, it stops and starts like randomly. If you watch those, yeah, I know you will watch them because you don't come live. But it stops and starts randomly. I'm going to keep an eye on this and make sure it doesn't stop recording. But I've closed all my 40 tabs on Chrome, so I think we should be good. All right, let's get started. I don't have to pack myself. Fucking great. Thanks. All right, compute the volume bounded below by the surface z equals. So in short, what is it? 3x plus what? 4xy squared?
2xy squared.
On what interval? Is it -1 to 1? Across 3, 4, 0, 3?
0, 3 cross -1 to 1.
Okay. So remember, in Calc 1, what did a single integral give you? One integral gave you area. So 2 integrals gives you volume, right? So if we want to find the volume, we just integrate the function, delta integral the function, 3x plus 2xy squared dA. By the way, if they want you to do the area between two surfaces, you do top function minus bottom function, right? And we're doing that in Calc 2. How do you find the area between two curves? You do top curve minus bottom curve and integrate over the bounds of intersection. If they wanted you to find the area between the volume between two surfaces, you do top surface minus bottom surface. Fortunately, they started giving us the bounds for x. So let's do the order dx dy. Let's do dy. dx dy. It doesn't really matter. When the bounds are constant, that's nice about when the bounds are constants, the order doesn't matter. The order is really easy. Just we did dx first, we had 0 to 3 first, and then we have -1 to 1 for y. So keep in mind that if the bounds if you do dy dx, you switch the order of the bounds. But the nice thing is that the bounds are constant, so switching it is no problem. We're going to find out that switching them is a lot harder than it is when they're not constant. But we'll deal with that later. I'm not going to integrate this. What can we? Let's do one. All right, let's do one. Integrate this with x 3x squared over 2 plus x squared y squared. Plug in 3, plug in 0, find the difference. That would be 27 over 2 plus 9y squared. I take that result and integrate it with respect to y. My head's in the way for a lot of this. I'm sure I'm in the way for some of you guys too. Sorry. Oh, I see it over here. All right, so this is correct me on my math if I'm wrong. I've got no crown to take. So 27 over 2 plus 9y squared. We're integrating that from what am I doing? From -1 to 1, right? This would be 27 plus 18, 45. Cool. I think I just did that in my head. I could have just making up numbers. 27 plus 18. Yeah. So the volume underneath this surface on the region from 0 to 3 and -1 to 1 would be 45. I do have to make sure that it's all always positive. Yes, it is. Okay, good. But it is. All right, we're set. All right, that was the first question. Quick, great, good job, done. All right, y e to the 2xy. It's a bit harder because the order in which you integrate might be preferred to do one order of integration versus another. Y e to the xy. Suppose for a moment that let's suppose we did dy dx. Now let me tell you. What?
Y to the 2xy.
Whatever. Yes. If I integrate with respect to y first, what technique of integration will I have to use?
Product rule.
Nope. Well, product was a derivative rule.
Integration by parts.
IBP, integration by parts. We have a y here and an exponential y. That means you have to use integration by parts. If I can avoid that, I'll try and do so. So let's do dx dy. I don't need integration by parts for this. So when I integrate y e to the 2xy dx dy, what's the integral of y e to the 2xy dy? So we treat y as a constant here. That's going to give us y e to the 2xy over, what's our constant coefficient of the x and the 2y? 2y. So we're going to divide by 2y. The 2y cancels and gives us e to the 2xy over 2. We're going to plug in our upper bound of, what were our bounds? 0 to 1 for y. Sorry, 0 to 2 for x and 0 to 1 for y. So we're going to do plug in 2 for x, plug in 1 for x, and then find the difference. So this gives us, plug in 1. I'm just going way too fast. E to the 2y over 2 minus e to the 0, which is just, well, let's get that as 1. So e to the 2y over 2 minus 1/2. Reasonable? Plug in 1, plug in 0, find the difference. And notice, I didn't have to use integration by parts to do that, did I? That meant the choice of integration that I chose was smart, right? Some people have said, could I do it the other way? And I say, could you have sex with a donkey? Yeah, you can, but it's going to be awful, right? So don't do that, right? So we say, okay, we're going to do the order dx dy. You have a problem with integration?
Calm down. Did you even integrate with y?
Not yet. I'm not done yet.
Oh, okay.
This is the result. Now I integrate this, right? Integrate e to the 2y over 2 minus 1/2 dy. It's just nothing but penis scalar for you guys always. 1.
Yeah, you wrote your bounds at 0 and 1 over there.
Didn't I? Didn't I?
Yeah, that's what
That's
threw
the
me
problem.
off.
Okay, that's fine. Yeah, that's fine. Yeah, correct me on that.
Well, jeez, you scared us out.
4. Okay, then we have e to the 4y over 8 minus y over 2, 0 to 1. Plug in 1, plug in 0, find the difference, and you get e to the 4th over 8 minus 1/2, and then subtract negative 1/8 gives you minus 5/8. That should be your answer, I think. I want to constantly stop and start this recording so I don't lose data. And I'll stitch it all together later. Alright. Good? Happy? Next one. Find the volume of the first octant bounded surface is z equals 4 minus y squared and x equals 3. So this is kind of hard because I don't explicitly give you the bounds. I tell you first octant, so that kind of implies a few bounds. First octant automatically means just that all the x, y, and 0 are positive. So when I say, as soon as you see the first octant, you might want to underline on your test. Underline first octant on your page here. This automatically tells you x is greater than 0, y is greater than equal to 0, z is greater than equal to 0. But I want the thing underneath 4 minus y squared. Let's do dy dx. What are my bounds on y? Are they given to me? No, they're not. What are my bounds on y anyway? Think of it this way. If I asked you to find the area underneath this parabola in the first quadrant, if I said y equals 4 minus x squared, what bounds would you integrate from? Clearly 0, because I said first quadrant, right? Up to where? Not 4, 2, right? 2 is where this guy intersects. So I was to integrate from 0 to 2. So it's implied that I would integrate from 0 to 2 because even though I haven't explicitly given you the bounds, I told you first quadrant. So you should think, okay, well, I want this to be in the first octant, meaning I want z to be positive. But since z is equal to 4 minus y squared, for what value of y does this switch from positive to negative? Which, 2, right? So 0 to 2 for y. I won't go any beyond y equals 2 because if I go y equals 3, I get negative values. And I don't want negative values. I want, again, first octant. What are my bounds for x? Did I give you any planes, any other information in the problem for x? 3. 3. Is that an upper bound or lower bound? What's my lower bound for x? 0. Cool? You guys can integrate that on your own. Is that good? The setup's fine though? Good. Next page. I'm trying to finish in under 2 hours. Compute the integral x e to the y. So this is over general region. So this is hard. This is much, much harder. This is those first 2 are a piece of cake. This one a little bit harder. So I say integral of y e to the x. Is that right?
X equals 1.
Great. Dyslexia. DA. And I say 0 is less than or equal to x is less than or equal to y. Y is dyslexia. Okay. What does that shape look like? Here's how I tend to do this. Let's cover up the right-hand side of this inequality. So I have 0 is less than y. What is the shape y equals 0? The line. What kind of line? Don't say straight. Everyone says straight. Horizontal. Everyone's straight, asshole. Okay. Y equals 0 is a horizontal line like this. This is y equals 0. You can even label y equals 0 if you'd like. Okay? Then we're going to cover up the leftmost and rightmost part of our inequality to get y equals x. Y equals x is what line? It's your 45-degree line, right? This is y equals x. From the origin, right? Passing through the origin. So there's y equals x. And then you have x equals 1. Okay, so I'm covering up the leftmost piece, and I get x equals 1. X equals 1 is the vertical line, x equals 1. So you get this nice, cute little triangle that we're going to integrate over it. And by the way, something I should mention. A lot of people don't understand what this means. Why am I integrating over this region? What does that even mean? Imagine that there's a surface coming off the wall, right? And I'm finding the volume between my hand, which is some wavy surface like x e to the y, and I'm finding all the volume between it and here, but only within this triangle. So it's got a triangular base, but it's got a wavy top, right? Who knows? I could. Imagine a triangle on the surface of this table, and then it comes up off, and you've got some volume, imagine some coffee. Coffee in this triangular prism with a weird top. And we're trying to find out how much volume is there. Cool? I find that volume by integrating the function, but over certain bounds. And the bounds are described here, and we're going to show how I do that using Calc 3. Cool? Alright. We're gonna show you there's two ways to do this. You can choose to integrate with respect to y first. So I want you to write two different integrals on your paper. You could do integral with respect to y first, then with respect to x, or you could do x and with respect to y. Let's start with y then with respect to x. Watch closely. I'm going to draw a line parallel to the y. Okay, watch. Once you're done writing, everyone look up. It says dy dx. This one says dy dx. Because it says dy dx, I'm going to integrate with respect to y first. I'm going to draw a line parallel to the y-axis. What do I hit first as I enter the region? Y equals what? 0. What do I hit as I leave the region?
Y equals x.
Y equals x. That's my upper bound. Okay? At that point, you ask yourself, once I've integrated with respect to y, I just ask myself, what's my leftmost value of x? What's my rightmost value of x? What's my leftmost value of x? 0. What's my rightmost value of x? 1. And on a test, they might say reverse the order of integration. They give you this integral, reverse the order of integration. How would I do that? Well, now I'm going to integrate with respect to x first. I'm going to draw a line parallel to the x-axis. What do I hit first? I hit y. Why'd you say y? Why not say x?
Because we're integrating with respect to x.
Good. We're integrating with respect to x. You better damn well not say anything that contains an x. That's something to keep in mind. If you're integrating with respect to x, your bounds better damn well not contain x. So integrating with respect to x, don't say y equals x. You have to say y. Notice we have said x here because we're integrating with respect to y. But because we're integrating here with respect to x, we're going to say y. Cool? And sometimes you're going to find yourself solving for one variable or another in this equation for this line to get the other. And then what do we hit as we leave the region? X equals what? 1. All right. Then, in the words of Ludacris, how low can you go?
0.
No one likes it? No? Okay. Thank you. In the words of the prophet Ludacris, how low can you go? Low is 0. How high can you go? 1. You shouldn't be surprised that both double integrals give you the same result. It's just a matter of preference as to which way you want to do it first. I like this way because look at what are our lower bounds in both?
0.
It's always lovely plugging in 0 as a lower bound for an integral because what tends to happen when you plug in 0 for a function? What do you get out? Most of the time 0. Not always, but most of the time. So that's why I like double zeros in my bottom. That sounds weird. All right, cool. Oh, one thing I wanted to mention is that was in the Facebook group, which was great. I've been telling my friends about this. Everyone, I said, listen, we're gonna do Tuesday, Wednesday at 6 p.m. Looks like it's gonna be 6 p.m. 7 likes. But then I said, someone reserve a room. Fucking crickets. Eventually, right? But it took 6 hours for this to roll around. But it wasn't like you guys were right there. Like you looked at the status. You said like, and then you didn't say anything after that. And then I posted what Katniss, I volunteer as tribute. Then I posted the Wikipedia article to bystander effect. That's fucking genius. That's comedy right there. You know what the bystander effect is? Like when someone's hurt, you're like, no, he'll call the police. No, he'll call the police. She'll call the police. No one does anything because everyone thinks someone else will do something. But that's comedy for me. All right. Anyway, cool. Next problem, right? Cool. Is that good? And then I implore you to do both of these integrals and show that they actually come out to be the same. If they come out to be something different, I seriously messed up or Calc 3 is broken. Okay. Problem 5. Find the double integral. We'll get there. Let's erase this because I want to put this kind of high on the board. The double integral of 6x cubed? Yes?
Yeah.
dA from where to where? What bounds? Y equals x is one of the bounds?
Yeah.
Y equals 2x?
X equals 2.
Okay. I'm going to draw a region. Sorry that I'm kind of in the way over here. Y equals x is this line. Y equals 2x is this line. X equals 2 is this line. So it's this triangle here. Now, I said before you can opt to integrate with whichever way you want to, which just means you're going to draw different horizontal lines. Let's suppose for a moment that I decide to integrate with respect to x first, then with respect to y. Don't write this down. This is wrong. This is wrong. Do not integrate with respect to x first, and here's why. As I draw a line parallel to the x-axis, because it says dx dy, what do I hit first? I hit some upsloping line, right? What do I hit as I leave the region? Some other upsloping line, right? But if I draw a parallel line up here, I hit the upsloping line, and what do I hit as I leave the region?
X equals 2.
Right, but not just an upsloping line. What kind of line? Vertical line. So I'm hitting two different curves as I leave the region. What do you think that means I need to do? Two different double integrals.
Fuck.
No. Yeah, he's already figured it. No, fuck that. So we're not doing two different double integrals. We're going to say, let's be smart about this and say, look, the region that we're, and a lot of professors will say this is a type 1 region or a type 2 region. Is this a phrase that he's ever used before? No? Yes? Type 1 region? Fuck, I don't care what that means. It just means I'm going to integrate with respect to one way than another, because if I do x first, I'm going to make up two different double integrals, and I don't want to do that. So now I'm going to integrate with respect to y. As I draw a line parallel to the y-axis, what do I hit first as I enter the region? What curve lower bounds my region?
2x.
Nope. 2x is the steeper line.
X.
Y equals x. That's the shallower line. What line do I hit as I leave the region? Moving on up. 2x. Moving on up. Alright. What's your leftmost value for x?
0.
0. Right. What's the value for x?
2.
2. And that's the setup. And with respect to y, you would get 6x cubed y, plug in 2x, plug in x, find the difference. That would be 12x to the fourth minus 6x to the fourth, 6x to the fourth. Integrate that from 0 to 2. dx, that gives you 6x to the fifth over 5. Plug in 5, that's 32 times 6 is 96 times 2, 192 over 5. Alright, miss the trash can in the way.
Yeah.
If you want to, you can try to ask your...
Yeah, you guys
Just
should
scoot a
sit
little
down.
right. I mean, of course, then as soon as I go over here, then the trash can's gonna be able to wait. So
I'll just switch back and forth.
yeah, right. Good luck. Of course, this probably doesn't matter too much. All that matters is the setup, and you can do the integration later. Good. Oh, this next one's really hard. Set up the integral, and this is nice because he's going to tell you to set up the integral and not actually do the integration, which is nice. That makes us happy. The less integration we have to do, the happier we are. 3xy dA. You're going to need to know some shapes. This is something I should have said at the beginning of the review, but you're going to need to know some shapes, some basic shapes. So it's going to piss you off. You're not going to be happy about this. Triangles are a little too easy. We have the curve x equals negative square root of 4y minus y squared. What the hell shape is that? Well, what I'm going to do is I'm going to square both sides. So I get x squared equals 4y minus y squared. I'm going to add y squared. I'm actually, everything goes, I'm going to rewrite this as. Okay, I'm going to complete the square. Oh, yeah, completing the square. Oh. So here we have, what shape is this? Good job.
It's a circle.
Circle, ellipse. Technically, you're also right because a circle is a type of ellipse, but more specifically, it's a circle. Circle with what radius?
2.
Centered where?
X equals 2. Y equals 2.
I need a coordinate.
0.
0, 2. Good. So a circle centered at 0, 2 with radius 2. Looks like that. Or, if you're familiar with Calc 2, it's r equals 2 sine theta. Or is it 4? Shit. 4 sine theta. Whoops. Don't worry about that though, don't write that down. Alright, so, keep in mind, all this algebraic manipulation was just to help us see what region this is, what shape this is. But notice, from the get-go, it says x equals negative square root of 4y minus y squared. So what part of this semicircle am I going to get? Shit. What part of this circle am I going to get? It's a semicircle. Which half? The left half. The negative implies I'm getting the left half. So you want to draw an arrow, left half. Huge deal. So I only want the left half of the semicircle. And then what else is there? There's also the line that says y equals 4 minus x. Y equals 4 minus x. Really convenient. 4 minus x is a line with a slope, slope of, so what do I want first? Slope is negative 1, y intercept is 4. So it looks like this. Looks like someone spilled their ice cream. Okay? What?
Let me thinking.
Well, yeah, but you give me these nasty. You give me like this, like
I was looking at the
shit
bullet
face. What is it? Like
point.
stank face. That's what it is. Anyway, what are we going to integrate respect to? X or y? Well, if you do y, what do you hit first? Sorry if you're watching online. It just stops. So I'm going to keep an eye. Try to keep an eye. We're on page 3. Why? So again, that's a giant list of integrals that you won't be able to do. but there could be many more, and there are probably many more. But to give you an example, there's a handful. Y cosine of 1 over x is one of them. Notice, you're not going to want to integrate with respect to x first because you just simply can't integrate cosine of 1 over x. No matter, try your hearts out, there's no way you're going to integrate cosine of 1 over x. It's not possible. So you're going to automatically want to integrate with respect to y. That's just kind of cluing you in, hey, try as you might, integrating with respect to x is not going to be possible here. So I'm going to integrate with respect to y. What are my bounds on y? X, y equals 1. Oh, shit. X, y equals 1. What else? X equals 3.
Yeah, x equals 5, y equals 0.
You're going to need to draw these. Now, the last three are pretty easy to draw. X equals 3 is a vertical line, right? Let's draw some axes. Sorry, I'm in the way. I'll move in a second. X equals 3 is this guy. X equals 5 is this guy. Y equals 0 is this guy. And then xy equals 1. I don't know what that looks like. Or maybe you don't. I'm going to rewrite xy equals 1 as y equals 1 over x. This should be a graph you know roughly what it looks like. Y equals 1 over x looks like this. Okay? Now we're only going to draw the piece that's in the first quadrant because it's the only time you're going to get any area bounded. But that's our region of integration. Cool? So this is y equals 1 over x. All right. I already mentioned that from the get-go, we knew we couldn't possibly integrate with respect to x. We're going to have to integrate with respect to y. As I draw a line parallel to the y-axis, what do I hit first? 0. What do I hit as I leave the region?
1 over x.
Y equals 1 over x. What's my leftmost bound for x? I think it's 3. My rightmost bound for x, I believe, is 5. Good. This integration I'm actually going to do out. The setup isn't important here. What's important is that you see that, hey, look, something that I couldn't previously integrate is not going to be possible. Integral of y is y squared over 2 cosine of 1 over x. I'm going to plug in 1 over x, I'm going to plug in 0 and find the difference. This gives me cosine of 1 over x over 2x squared. Integrate from 3 to 5. I probably won't integrate that, but I will tell you what you need to do. 1 over x sits here. What do you see in the denominator? That's an x squared, right? Namely, you see a 1 over x on the outside. Guess what the derivative of 1 over x is? Negative 1 over x squared. So what do you think you're going to need to do here? U sub. If you make a U sub with choice u equals 1 over x, and therefore d was negative 1 over x squared, this transforms the integral into the integral of cosine of u with a negative and a 2 on the bottom, which you can easily integrate. Once you integrate, you'll plug back in the 1 over x, then plug in your upper bound, plug in your lower bound, and find the difference. Good? But the beauty of this problem is that cosine of 1 over x couldn't be integrated to begin with. And yet when we integrated with that guy with respect to y, it spat out something that then allowed us to use a u sub. The same thing over here. 1 over the square root of x cubed plus 1. I don't think, oh yeah, okay. This is a bit harder, because anyone need this still up on the board? Okay. This one's a bit harder because I didn't explicitly give you the bounds of integration. I gave them to you in the integral. So integral 0 to 4. Integral square root of y to 2, and I believe it's 1 over square root of x cubed plus 1 dx dy?
Yeah.
Okay. This is, I don't know if this is one of the ones on the top of the page. It's not, but guess what? Oh, yeah, it is.
Yeah.
Guess what? Try as you might, 1 over x cubed plus 1 is not going to be easily integrable. If that was an x squared, you might have a chance because it's a trig sub, but it's x cubed, and it's not going to be pretty. So, what we're going to do instead is say, hey, look, we're going to reverse the order of integration. But the bounds are implied inside the... Remember, last time I gave you the problem was like, here's one bound, here's one bound, here's one bound, here's one bound, draw your picture, draw your lines. I didn't do that this time. They're already encoded in the integral, so we have to decipher them from the integral, like so. It says integral with respect to x first, so as I draw a line parallel to the x-axis, what do I hit? It tells me I hit what? Root y. I hit x equals root y. Then what do I hit as I leave the region? X equals 2. X equals 2 is a vertical line over here. X equals square root of y is better known as what?
Y equals x squared.
Y equals x squared, a parabola like this. We can get the left-hand side if you want to, but that's kind of relevant. Right? And then what are our bounds for y? How low can you go? 0. And then 4 just so happens to be the intersection. I mean, what happens when you plug 2 into x squared? What's y equals 2 squared? 4. So this coordinate is 2, 4. And so you get this region. You're deciphering what the region is based on the bounds already given. Does anybody need me to repeat how I did that? Okay. But again, Drawing a line parallel to the x-axis, I hit square root of y first, then I hit x equals 2, and then I do bottom to top for lower to top. I don't just say the constants. Okay, now we have to reverse the order of integration. Now we're gonna shit. Blue, you're awful. Gone. Forget it. All right. Now I draw a line parallel to the y-axis. What do I hit first? What do I hit first into the region? 0. What do I hit leaving the region?
Square x.
You don't say x squared, right? So you can say square root of y, or you can say x squared. How far left can you go? 0.
0.
How far right can you go? 2. So this is dy dx now, right? When I integrate this with respect to y, I get y over. Actually, yeah, really quickly, y over square root of x cubed. I'm not gonna spend too much time on this. Plugging them down, I get this. What can I do with this? How can I integrate that guy? U sub with u equals what? X cubed plus 1. Exactly. Make sense? So u subs are popping out that weren't previously there. Make sense? That's what's going on with these problems. Do u sub. Right. Okay. What's the next thing say? Polar. Not bad. All right, here are the rules of polar. X equals r cosine theta. They're at the top of the page, but I'm going to use them frequently. The first problem says integral of, volume underneath z equals 16 minus x squared minus y squared above the x by plane. So, by the way, what shape is this? It's a paraboloid. Good job, guys. This happens every semester, is that no one knows what shapes we're talking about. So z equals x squared plus y squared. It's a paraboloid. Looks like this. Looks like a bowl. You don't have to draw them. You can draw them out if you want to, but there will be a page, about 3 or 4 pages, that has all these listed out. So 16 minus x squared minus y squared is one that opens downward, right? It's flipped it upside down. It looks like this. Okay. Basically, we want the volume underneath that dome shape. All right? How can I find it? Well, I'm going to do the double integral of 16 minus x squared minus y squared. What's my lower function? You could argue that it's z equals 0, so you could say this thing minus 0 if you want to, because it's unnecessary. The lower surface is 0. dA. Now, as soon as you see an x squared plus a y squared, or a negative x squared minus y squared, you should think polar. Polar integral is going to make this thing a lot simpler. And besides, if we're going to look at the top-down version of this, what would we see? What would we see if we looked at a top-down view of this thing? A circle. What are the bounds in the circle? Well, you could say y equals square root of 16 minus x squared, and the lower bound would be negative. Don't write this, by the way. Y equals negative 16 square root of x squared, square root of 16 minus x squared, and then integrate over those bounds. Is that going to be fun? No, it's going to be a fucking nightmare. So we're not going to do that. We're going to convert to polar. So we say, all right, anytime I see an instance of x squared plus y squared, it becomes r squared. And our conversion from dx dy or dy dx whatever is what? R dr d theta. Is this familiar to you guys? R dr d theta? Anytime you convert from Cartesian dx dy to polar, you're using r dr d theta. You might even say that r is the Jacobian into polar coordinates. But that's a term you probably learned today and you want to learn more about later. Cool? I'm not going to talk too much about that now, though. So r is your Jacobian. Double integral of 16r minus r cubed dr d theta. What are my bounds on r? This is a circle with what radius?
2.
What? 4. Radius 4. So 0 to 4. Are there any other restrictions on where I want this? So I say first octant or some shit like that? Nope. But if I had said, okay, so I want the whole circle and nothing about the circle. So help me God. So 0 to 2 pi. But if I had something like first octant, what would I have said? 0 to what?
0 to pi over 2.
Pi over 2, right? Because first octant would give me the first quadrant, so I have 0 to pi over 2. I could have said something like this. Y is larger than or equal to 0. What would that mean? What bounds for y would I get? Or what bounds for theta would I get? 0 to pi. But if I said x is greater than 0? Negative pi over 2 to pi over 2. Right? Negative pi over 2 for these watching at negative pi over 2 to pi over 2. Okay? Don't say 3 pi over 2 to pi over 2 because that's bigger to lower, but then you'd be going backwards, so it's all fucked up. So negative pi over 2 to pi over 2. Cool? Good on that. Make sure that if they say some sort of like first octant, x is positive, y is positive, that you modify your bounds on theta accordingly. This is a great one. I love this one. Find the volume between the graphs of e to the negative x squared minus y squared and z equals what? 1 over the cube root of e?
Yeah.
I'm going to pause the video real quick. I got to say something to everybody in this room that you can't hear. And you'll never know that secret. Okay. All right. Unless someone rats me out. Okay, so, but, you know, stitches get stitches. All right, so we have to figure out which one's on top, which one's on bottom. It's kind of hard to do. What the fuck would I ever tell you which one's on top and bottom? Shit. This problem's a little too hard. You're going to do the double integral, upper function minus lower, upper surface minus lower surface. I don't know how you would know which one's on top versus which one's on bottom. They would probably have to tell you. But let's just tell you that I'm going to tell you this one's on top, and 1 over the cube root of e is on bottom. So minus 1 over the cube root of e. So top surface, bottom surface. You subtract the surface on that's underneath. You subtract the surface underneath from the one that's on the top to get the volume between, and you integrate over that region. And the question is, how can I figure out the bounds of integration? How did you ever figure out the bounds of integration when I said, I want you to find the area between the curves y equals x squared plus 2 and y equals 3 minus x? What did you do to figure out the bounds for these, the integration, the area between these two? You set them equal. We're going to do the same thing here. E to the negative, we're going to say r squared while we're at it, right? Equals, what is the, how might I write 1 over cube root of e? E to what power? Negative 1/3. The cube root. Cool? So, we have r, if the bases are equal and the functions are overall equal, then their exponents are equal. R squared equals 1/3 means r equals root 3 over 3. There's something to be said for, well, could you say plus or minus root 3 over 3? Yeah, but radii are usually taken to be positive numbers, so r equals root 3 over 3, excuse me. Okay, so that means when we convert this guy to polar, e to the negative r squared minus 1 over cube root of e. What do I have to tack onto this? RD theta, wonderful. My bounds for r go from, doesn't seem there's an upper bound, it's just implied that my lower bound's what? 0. We're looking at a circle of radius root 3 over 3. Did I say first octet or anything like that? I say y is positive though. So my bounds from theta go from where?
0 to pi over 2.
Just pi. Pi over 2 would be first octet. Pi is the first and second quadrant, which is what we want. How do you integrate e to the negative r squared? It looks like one of those integrals we had a few pages ago. E to the r squared can't be done. But if you have an r here, we do. How can you integrate e to the r e to the r squared? U sub with u equals negative r squared. Good? Cool. So you write down u sub, do the u sub later. Sorry I don't have answers for you. I should have worked this out beforehand, but setting up is the hard part. The integration is not the hard part. Some people will say speak for yourself. Now what are we on? More polar? I hope it's not more polar. Okay. This was actually going to require integration by parts. Alright, I'm going to cover everything in polar right away. I see the x squared plus y squared immediately means to me, hey, why not use polar? So this is r cubed on the bottom times r d theta. Go and write that all down. The r sine theta is the numerator. X squared plus y squared is r squared, but because it's being raised to the 3/2, it becomes an r cubed. And my conversion from dA to dr d theta is r dr d theta, which will boil down to basically sine of theta over r dr d theta. Now I wrote this problem in a dream, or I saw it in a dream, and I hope it works. I don't know if it's actually integrable, but I hope. My bound's on r. Ooh, okay, this is why this is hard. R equals 1 and r equals 1 plus cosine theta. It's been a while since you've seen this stuff, so get bright-eyed about it. Here's r equals 1, it's the circle center of the origin of radius 1. What is r equals 1 plus cosine theta?
Oh god.
What shape would we call that? The r equals 1 plus 1, or 1 plus cosine theta. Starts with a C, rhymes with ardioid. Cardioid.
That was way too long ago.
You might need to review your polar curves. So grab your Calc packets.
Yeah.
right? Okay,
Is stuff like this on the test? You feel like that's correct?
it's possible. This separates the A's from the B's. But if it happens at all, it might not happen whatsoever. I mean, let the practice test that I give you in the back be a guide. But if it's not that, if you don't see any of those problems in your practice test that I gave, which I didn't bother looking at them, I probably should have. I don't remember being one like this, but one time over the course of 3 semesters I was feeling like this. So yeah, it's worth doing. How do I figure my bounds for R? It's a little bit different than how I figured out for X and Y, right? Here's how I do it. Watch carefully. Instead of drawing a line parallel to the y-axis or parallel to the x-axis or anything like that, I say, as I draw a ray out from the origin, what do I hit first? Which circle? R equals, well, yeah, there's only one circle, but I mean, which curve? I call it R equals 1, right? What do I hit as I leave, and this is the region in question, right? This guy. What do I hit as I leave the region?
1 plus cos.
1 plus cosine theta. Cool. What are my bounds on theta? And what quadrants do you see that region? 1 and 4, right? And it is flush up against this, but keep in mind that you might have to set, I mean, you ought to set 1 plus cosine theta equal to 1 to figure out where they intersect. Subtract the ones over, you get cosine theta equal to 0. When is cosine theta equal to 0? Pi over 2 and negative pi over 2, right? So that tells you your bounds for theta. Should have done it over here, whatever. Oh, this isn't, yeah. Okay. Alright, let's do the integration. The integral of this, it becomes sine theta, ln of 1 plus cosine theta, minus sine theta, ln of 1. What's ln of 1? 0. That goes away. How do I integrate sine ln of 1? Oh, this is no parts. This is u sub. But you would say, once again, u equals 1 plus cosine theta. So, oh yeah, you actually do need parts. Never mind. du equals, that's why I gave you the integral of ln of x at the bottom of this page. So this transforms the integral into negative ln of u. What's the integral of ln of u? What's the integral of ln of x? I wish it was somewhere on this page.
X ln of x minus x.
Yeah, so this would be negative u ln of u plus u. If I replace u by 1 plus cosine x, I get 1 plus cosine theta here, ln 1 plus cosine theta here, plus 1 plus cosine theta from negative pi over 2 to pi over 2. Should I go ahead and figure out what that number is? Yeah, you guys can do yourself. Great. What page are we on? 5? Are we now ready yet? Good. I think that's 12 pages. I think. Yeah, ish. Okay, keep going. Maybe 14. Alright. Oh, one more thing. Remember how I said as you draw your ray from the origin, you ask yourself what you hit first on your way into the region? That's your lower bound? Your lower bound, if by the way, so let's suppose for a moment that the region you were asked to integrate over was a circle. As I begin to draw my ray, notice that as I begin to draw my ray, I'm already inside the region of integration. What does that mean my lower bound is? 0. As I begin to draw my ray, I'm already inside my region of integration, so that means my lower bound for R is 0. Keep that in mind. Here, I wasn't already inside my region of integration, so my lower bound was not 0. Do you need me to explain that again?
Yes, please.
Sure. Circle. Remember I said before, draw a ray from the origin. As I draw it outward, what do I hit first? I hit the circle. That means my lower bound. As I draw a ray here, as I draw my ray, I'm already where? I'm already inside the shaded region. So what does that mean about my lower bound for R? It's automatically, yeah. Cool.
If you had said y or x is greater than 0, whatever, that made it only in
The right hand side?
Yeah.
I don't think I needed
How
that
would
though.
you have done that?
No, I don't think I said that, did it? I don't think the problem said that. The previous problem did. I think the problem with the previous page did. Or am I wrong? I think I'm not wrong. Okay. Triple integrals. Am I crazy? You ready? Am I right? Okay, cool. Triple integrals. You're going to see this problem tomorrow, roughly, if I change the numbers. X cubed e to the y cosine 2z. Wait, e to the y cosine 2z. The nice thing is I've given you a constant balance, let's say dz, dy, dx. I always like reverse alphabetical order for integration. I don't know why, that's just how my mom raised me. 0 to pi over 4. 0 to 1. 0 to 1, 1 to 3. 0 to 1, 1 to 3. Now this looks like a lot of work, right? One integral followed by another, followed by another. A lot of integration. So the way we can, here's a really cool trick that I think is at the bottom of this page. If the function given to you can be split as a product of a function of x, a function of y, and a function of z, which is can. X cubed times e to the y times cosine of 2z. Does this guy have any y's or z's in it?
No.
No. Does this guy have any x's or z's in it?
No.
No. Does this guy have any x's or y's in it? No. I can just break this apart into 3 different integrals. So long as what else needs to be the case? You can read that little blurb at the bottom. So long as something about the bounds.
Bounds are constant.
The bounds are constant, which these are. So 1 to 3, 0 to 1, pi, and 0 to pi over 4. So 1 to 3, 0 to 1, 0 to pi over 4. This actually makes this a lot more palatable to me because I'm not writing so much. If I integrate this, I get x cubed, e to the y, cosine 2z all over 2. Then plug in pi over 4, plug in 0. Then I get x cubed, e to the y, cosine pi over 2, minus, right. This gets really tedious really quick. This is x to the 4th over 4, 1 to 3. This is e to the y, that's it, 0 to 1. And this is sine of 2z over 2, 0 to pi over 4. So this is 3 cubed, so 3 to the 4th is 81, minus 1 is 80, so this is 20 times e minus 1 times, because sine of 2 times pi over 4 is pi over 2 times, or sine of that is 1, 1/2. So I get an answer of 10 times e minus 1. That's the result of this integral. What's the question asking?
Average.
What? The average value, right? So in much the same way that when you're asked to find the average value of a two-variable function over a certain area, you divide by the area of that result, the integral. If you're asked to find the average value of a triple integral, or of a 3-variable function, you compute the integral and you divide by the what? The volume encapsulated by the bounds. So what's the volume of a box whose width length from 1 to 3, length goes from 0 to 1, and height goes from 0 to pi over 4? Length times width times height, right? So what's the width? 1 to 3. How much of a distance is that? 2. What's the length? 0 to 1. 1. And height? 0 to pi over 4? Pi over 4. So whatever that comes out to be should be 20 times e minus 1 over pi. And that's the average value. Good? Alright. Evaluate. Oh, I fucking hate these so much. I just want to skip these, right? Oh. Stop start. Alright. These are the hardest ones you already have to do. Spherical and cylindrical are actually easier by comparison, which is kind of odd because you think later would be harder, right? No. Earlier is actually, or right in the middle is harder. So, I fucking hate this so much. We're just going to skip it and come back to it later. No?
Let's just get it over with.
What did some of you guys forget? Was it 2x dv? Let's, as I say, do dz, dy, dx. I just like it the best. Alright. Now, x plus y plus z equals 4. What shape is that?
Sphere.
Probably.
Nice.
God, you guys are really disappointing me. There's none of those are being squared, by the way. X nor y nor z are being squared, so there's nothing curvy about it.
It's just a line.
Not a line.
Plane?
Yes!
Oh,
Plane!
it's plane.
X plus
that's
y
right.
plus z equals 4 is a plane. Go ahead and put that under there because you guys are bad at that. Okay.
Oh, that
That's
was
a plane. Alright?
This is terrible.
Test 2 is a long time.
Yeah. Pre-calc was a long time ago, but I still remember it. That's actually really fucked up. Alright, x plus y plus z equals 4. Here's what it looks like. Here's a nice thing. If all these coefficients are positive, here's what this region looks like. It just forms like a pyramid. Where's my red marker? Oh, okay. What do I want to do here? So this is a little bit harder. As I draw a line parallel to the z-axis, this is coming from up underneath, this is coming from up underneath the table, right? So think of this as the xy plane. The ray comes up and hits the xy plane. Beep, right there. Makes that noise when it does it. So it hits z equals 0. Alright? Then what does it hit as it leaves the region?
4 minus x minus y.
4 minus x minus y. Good. You solved for z in this equation. Hit the plane, and the plane has the equation x plus y plus z equals 4, but you don't want to write it like that. You got to write it in terms of z, or solve for z. Cool? Now then, here comes the hard part. Once we've eliminated the z variable, we now look at a collapsed version of this. We're removing the z variable. So we're looking at we're looking at a collapsed version of this. There we go. That's the words I want to use. We're looking at a collapsed version of this. So we're looking at basically this guy here. Turns out the equation of this line is y equals 4 minus x, because after all, where do you see this triangle? It's in the plane z equals 0. So we plug in 0 for y, and you get, or plug in 0 for z, and you get y equals 4 minus x. So we're going to draw, because the next step is with integrating with respect to y, we draw a line parallel to the y-axis. What do we get first?
Y equals 0.
0. Then what do I have to leave the region?
4 minus x.
4 minus x. What's my leftmost value of x?
0.
Rightmost value of x?
4.
0 to 4. Don't integrate it, it's just going to be a heartache, right? Next problem. Yeah, this one's rough. Okay, ydb. Here's a tip you're going to want to use. Look for any bounds that are constant. Did I specify any bounds that were constant? Y. So I'm going to do that one last. I'm going to do dz, dx, dy. I'm going to do y last, and my bounds in that from 0 to 4. Isn't that nice? Just give those for free. If you have constant bounds somewhere, make that your last order of integration. ydb. So y goes here. How about my bounds for z? Well, do I have a z equation? Z equals something? Yes, I do. Z equals 2 minus x. Is that my lower bound or upper bound? Why is it not my lower bound? Or what is my lower bound?
0.
Yeah, okay, I did use. Okay.
Mm-hmm.
Okay, so 2 minus x and z equals 0.
How would you know that if you didn't have it?
Typically, okay, you have to ask yourself, what kind of bounds does x take on? Now here, this is kind of hard to do. If I said x was between -4 and 0, how would I? Oh shit. Let's say 2 and 4. But if x is between 2 and 4, which is larger, 0 or 2 minus x?
Sometimes.
No, actually, no, not sometimes. Always, because 2 minus x. Right. Well, then it was a match. So it doesn't matter if it's a match. But any other time, an infinite number of times, infinitely more times than when it's x is 2. Any other time you choose the value of x between these two values, this value is negative. So this is upside down. Does that make sense? Because you should go from smaller to bigger, right? Now, how can I be sure that 2 minus x is bigger than 0 here? Well, what do I know about x? X goes from where to where? Or x? What x is equal to what?
Y. X squared equals Y.
X squared equals y, so y equals the square root of x, right? And if x takes a value, or if y takes on values between 0 and 4, x takes on values between 0 and 2. And if you take on the value, if x takes on the value between 0 and 2, then 2 minus x never takes on the value that's negative. It'll be positive. So I'm sure that 2 minus x will be above 0. That's a lot to say. But basically, I'm sure that 2 minus x is going to be above 0 because x only takes on values that are positive, or never larger than 2. All right, how about bounds for x? I believe 0 would be 1, and square root of y. Good. I think you're set up. Cool. Happy? Moving on. Yeah, there's our graphs, our all graphs. This is cylindrical coordinates. Oh, one thing, gotta pause and okay. I drew these, or you can use a program called Grapher. They're gonna look eerily reminiscent to something you'll see later. Just maybe like rotated or something. So evaluate triple integral of 2 over z. We're using cylindrical coordinates here, so that means we're going to convert this to triple integral of 2 over z. What's my conversion for cylindrical coordinates? It's just like polar, except that instead of r d theta, it's r dz d theta. This is kind of a hard problem. Now, the equation z equals 2e to the x. God, I hope this is actually going to break now. Oh, maybe not. You can't say e to the x anymore. We're not in Cartesian, we're in polar. So we have to say z equals what? 2e to the what? What is x in terms of polar coordinates? R cosine theta. So that's what we're going to have to say for that. We also have z equals 2. And the question is, What do my bounds for z will be a little tricky. 2 versus 2e to the r cosine theta. Well, depending on the exponent here, you could get numbers that are less than 2 and some numbers that are larger than 2. But how can I be sure that this is always going to give me values that are larger than 2? Because I say something like nothing. Fuck. Oh, I say below. Oh, that's nice. Whew. Whenever I use words like below, then I tell you automatically this is above. That works. Okay, good. So 2 and 2e to the r cosine theta. Does that make sense? When I use buzzwords like I want something below this, but above z equals 2, it's telling you your lower bound is z equals 2, and it's telling you this guy's your upper bound. That makes sense? How would you do it without that? You wouldn't. I have to give you some more information, like only look at positive values for theta or positive values for r. I don't know, something crazy like that. Okay. Bounds for r. It says enclosed by the two cylinders x squared plus y squared equals 1 and x squared plus y squared equals 9. What are the radii of those cylinders?
1 and 3.
1 and 3. And here's where it gets a little tricky. If you look at the top-down view of the graph, which is the second picture you see two concentric cylinders, right? But only for half of that graph is it the case that the exponential 2e to the x is above 2. There's only one piece of that graph for which 2e to the x is actually above 2. Think of it this way. What's the value of e to the x at x equals 0? 1, and then times 2 is 2, right? So you get 2 is larger than 2, which isn't true. But basically, that's the breaking point. There are some values, if I let x be positive, like something like 1. What's e to the 1?
0.
E to the 1.
E.
E. E to the 0 is 1, e to the 1 is e. E to the 1 is e like 2.718 times 2 is 5.4-ish. 5.4 is larger than 2, right? So for positive values of x, this inequality is true. What about for negative values for x? What about negative 1? What's e to the negative 1? 1 over e, which means like 2 over 2.7 is, let's say 2 over 2.7 is 1. Gross amounts of rounding. 2 over 2.7 is 1. Is 1 larger than 2? No. So negative values of x aren't allowed. It must be the case that x must be positive. But that's fine. You mean like, okay, to be technically correct, yeah, x is larger than 0, but it doesn't change anything as far as the bounds go. You'll still have x larger than 0 means this side of the unit circle, and then what bounds theta do you get there? Good. And that's your setup. Good? How are we doing? Oh, 1 hour down. 1 hour, and we're more than halfway through, I think. Good. Okay, this one's cool. Compute the triple integral to cylinder coordinates and evaluate x cubed plus xy squared. X cubed plus xy squared is the A triple integral. So I gave you a bunch of, let's do it without the pictures, or let's try to pretend like we can do it without the pictures. Z is underneath 4 minus x squared minus y squared. Basically, shit. Gotta convert this a lot. We're gonna do a lot of conversion here. Notice this looks like x squared plus y squared, right? But I can factor something out. What can I factor out?
X.
And if I factor out an x, what am I left with? X squared plus y squared, which is r squared. So I'll have a factoring out an x, which is an r cosine theta. I'm left with an r squared. And my conversion from dA to zr theta is r dz dr d theta. And it sometimes helps me to do this. To write like underneath, this is what this piece came from, this is what this piece came from. That way I don't get lost. That helps me kind of see visually where things come from. So I have the triple integral r to the 4th cosine theta dz dr d theta. What are my bounds on z? Well, it says that in the first octant, or no it doesn't, but it says z is greater than 0, right? So there's 0 is your lower bound for z. What's your upper bound for z? Z is upper bounded by z equals 4 minus x squared minus y squared. But we can't say 4 minus x squared minus y squared. We have to say what? 4 minus r squared. Does that make sense? You're not supposed to say 4 minus, you can't use the letters x or y anymore. You have to use r's, thetas, and z's. So 4 minus r squared. What about my bounds for r? Think of it this way. If you take the paraboloid, which is downward opening like that one, so you can kind of see what kind of shape does it form when it intersects the xy plane? Circle, like a 3/8 circle, right? What's the radius of that circle? Well, if I take 4 minus x squared minus y squared, which is, this is z by the way, right? This is z. And I intersect it with z equals 0, then I set these guys equal, right? When it's 4 minus x squared minus y squared equals 0, I get x squared plus y squared equals 4, which is a circle over what radius? 2. 0 to 2 for my bounds for r. How about theta? I gave you some planes that kind of tell you how that goes. Well, let's again pretend we have pictures. We said y is less than x, so here's y is less than x. Or y is equal to x, right? And then I also said what? X is larger than 0. X equals 0 is the vertical line. So I want everything to the right of this line, but underneath this line. So basically this. And that's kind of what you see in the pictures, right? Now what bounds on theta are those? Straight down would be what corresponds to what value of theta? Negative pi over 2. And this would be what? Pi over 4. So those are your bounds on theta. How's that? Good? Problem 17. Convert. Got a door knocker. Convert the triple integral into cylindrical coordinates. This one's a pain in the ass too. Oh, by the way, I'm putting this all online on my YouTube channel. I don't know what that YouTube channel is, Andrew Eleanor. I don't know, but I'll post it in the group too, so you can see it and share it with your friends. Cool. All right. This one's a good one. 0 to 2 was it negative square root of 4 minus y squared?
Yeah, I don't think that's.
No, it's not. And then negative square root of y squared, x squared plus y squared. And then square root of 4 minus y. Okay. Y squared dv. We're going to convert this to polar, or cylindrical. So we have r squared, r cubed, sine, and by the way, he's going to do this shit to you all the time, watch. R squared sine squared theta, dz, dr, d theta. One of the answer choices will be this, and you're going to look at the bounds and go, oh, well shit, do the bounds match? Doesn't fucking matter if the bounds match or not, because at this point, he's fucked up. Y squared contains an r squared, and your conversion from dv to rz theta would contain an extra factor of r. So any answer that doesn't have an r cubed sine theta is wrong, or sine squared theta. So it's better damn well be sine cubed. And you will be able to eliminate a lot of answers based on that. You have to make sure that the conversion was made correctly, not just the bounds, but just to make sure the integrand was converted correctly. You're going to see on some of the old tests, you're going to see half the answers are incorrect integrands, and half the answers have incorrect bounds. So then whichever one's left is the one that is right. Cool? So eliminate based on that. Anyway, going back to this. The nice thing about the bounds for z is that they're pretty easy to do. What's this guy? Negative r, right? What's this guy up here? Square root of what?
4 minus y squared.
Square root of 4 minus r squared. Now, these are a bit tougher. These outermost two. How do these look? We're going to try and figure out what shape this gives us. Ooh, green looks good. All right. Negative square root of 4 minus y squared. What would that give us? What shape is that? Do I start with x? What's that? Yes. Not the bottom. You'd be right if it was 4 minus x squared, but it's 4 minus y squared. Square root of 4 minus x squared, or negative that thereof, is the lower half of a semicircle. So x equals negative square root of 4 minus y squared. It's actually which side? Left side. So you're going to get the left side of the circle. And what about your bounds for y? Your bounds for y go from where to where?
Pi over 2 negative.
Wait, shit. What did I do here? Oh, you know what? This problem's all wrong. Slightly. We'll fix it. Change the dv. Change dv that's tacked on to dz, dx, dy. Okay, that's better. Kind of obvious because these better damn well be bounds for z because they certainly couldn't be bounds for x or y. These couldn't be bounds for y because it has a y. So these must be bounds. These must be bounds for y. What are your bounds for y? They go from where to where? 0 to 2, right? So that means you're getting 0 and 2. So this piece of the circle. Alright? There are many different ways I can describe different quarters of the circle. But this tells me the left semicircle, and it terminates here. And this tells me the lowest bound on y is 0 and the highest bound is 2. So it's giving me this. What if, okay, so with that in mind, let's go ahead and figure out the bounds for r. R goes from where to where? What radius is this? 2. So 0 to 2 for r. What are my bounds on theta? Pi halves to pi. Cool? What if this was said, instead of negative square root of 4 minus y squared, it said negative to positive square root of 4 minus y squared? Well, that would be the whole circle, and I would be getting this as well. Make sense? I could change this. I could have said, instead of 0 to 2, I could have said negative 2 to 0. What would that give me? Well, instead of getting this upper part, I would have gotten this lower part. Make sense? Cool. Keep going, turn the page. Any questions on that, by the way? Stop, start. Oh, spherical coordinates. I actually didn't label this page spherical coordinates. If you want to, you can label spherical coordinates in bold. But I mean, the first 3 words contain the word spherical coordinates, so we're good. You're going to need to memorize these. Some of the questions in the passage has been convert the polar the spherical coordinate 6, comma pi over 4, comma pi over 3. Convert that spherical coordinate into Cartesian coordinates. So it just means this would be phi, and this would be theta, or that's what I do at least. There's rho, phi, theta. So you take 6 times cosine pi over 3 times sine pi over 4, that's your x coordinate. Then you take 6 times sine pi over 4 times sine pi over 3, that's your y coordinate, and so forth and so on. So it's simply just straight up convert, which is sometimes they might ask you to do. I didn't give you conversion from Cartesian to spherical, but that's kind of hard. Might be interested in looking that up, or if you're curious to know, ask on the Facebook group. Cool, alright.
Could you just take like the regular one instead of equal to each other? Like
You would have to do something a little bit crazier, like rho, cos, no. It would take a little bit of work. Yeah, it would take a lot of work, actually. There might be you can just look up spherical coordinates, or just like, here's what you can do. Look at the answer choices, and then convert those all to Cartesian, and whichever one matches the one they give you. Of course, that would take some time. But I don't know how you would do it otherwise, or at least not an easy way, not a quick way. Anyway, here's where I embarrass myself. So, spherical coordinates, we know rho is just your 3-dimensional radius. R was 2-dimensional radius, rho is 3-dimensional radius, so it incorporates the z direction. That's why r squared is x squared plus y squared, and rho squared is x squared plus y squared plus z squared. Cool? Theta is our usual lateral angular movement, right? Phi is as it was called the azimuth, and it comes off the vertical. Now, here's what's weird about this, is that it's more like a, alright, I'm going to embarrass myself. It's like a ballerina, so it's like it's blossoming, like this. Sorry, I have to do this. But, what am I going to say? We know that if I talk about theta being pi over 4, it's this angle here. Don't write this. Pi over 4, right? It comes off an angle pi over 4 from the x-axis. If I talk about theta equals pi over, if I talk about phi equals pi over 3, or pi over 6, I'm talking about an angle like this off the z-axis, but not just this angle, and this, basically all these angles that form like a conical shape. Every angle I make with all these rays that are coming off the z-axis have an angle of pi over 6 with the z-axis. So it's like a blossom. It's like a blooming flower. And so it's like spinning around. Alright. Like a pirouette of sorts. Okay. So with that in mind, the nice thing about this first one is that I've kind of given you kind of the rundown of how this works. I took the time to write out how that breakdown works. So we have the triple integral of x, y, dv, right? Well, x is equal to, if you look down at the next line, rho cosine theta sine phi, right? That's x. And then I have times rho sine theta sine phi, that's y. Then I have rho squared sine phi d rho d phi d theta. Rho squared sine phi is your conversion from Cartesian to spherical, so keep that in mind. Rho squared sine phi. They might just ask you, what's the Jacobian for spherical? True or false? Jacobian for spherical is rho squared sine theta. True or false? False. It's sine phi, right? 2 points. Cool? He's done that in the past. Alright. So, I've converted, this is what you should do. Whenever you tackle a spherical coordinate integration problem, you can see something like x times y times dv. Convert each of the individual pieces into rho sine phi, sine cosine theta, whatever you need to do, right? So, and then I multiply that all, and it gives me the triple integral of rho to the 4th, which I've already got there. Rho to the 4th, I'm going to rewrite the rho to the 4th part. Cosine theta, sine theta, sine to the 3rd of phi. D rho, d phi, d theta. Okay, bounds on rho. Rho is your radius of the sphere. What sphere is it? What's the radius of our sphere? Good job. 4, radius 4. X squared plus y squared plus z squared equals 16. So that tells you radius for the sphere. What are our bounds on phi? This is kind of tricky. It says inside the cone? Above the cone, okay. So pi over 6, this is what I mentioned before. Pi over 6. Let's put it this way. Phi equals pi over 6 describes a cone. Let's write that down. And in general, phi equals some number, or phi equals an angle, describes a cone. Phi equals 6 describes a cone that looks like this. It's kind of narrow. Because after all, pi over 6 is your one of the smallest angles you know besides 0. It looks like this. If you'd like to draw it, you can. So here's the cone. It's a very steep cone. Pi over 6. And this is all tucked on the inside of a sphere, so we're going to draw a sphere around this as well. So I'm looking, the region in question is this ice cream cone. Okay? This guy. That little cocoon there. Alright? So, as you can see, and by the way, let's use the same mentality that we use for polar coordinates. As I draw a ray out from the origin, upward through my region of integration, I'm already inside my region of integration, hence my lower bound for rho is 0. What do I hit as I leave the region? The cone of the sphere. Sphere. The cone, don't think of the cone as having a bottom, it's an open cone. I won't hit the cone, it's hollow. So I hit the sphere on the way out. Notice I don't, you can say I don't hit this, I'm trying to convey that this is inside the cone. So, and then think of it this way, if you were on the inside of an ice cream cone, you looked up, you would see the ice cream, right? The ice cream top. Ice cream paint job. Alright, so, how about phi? Phi goes from where to where? Sorry, I've stopped recording. Alright, this corresponds to what phi equals, thanks for catching that by the way, pi over 2, right? So, if I said underneath the cone but above the xy plane, I would say from pi over 6 to pi over 2. Does that make sense? But I want above the cone, so it's going to be 0 to pi over 6. Good? And then what are my bounds on theta? Do I say first octant or anything like that? First octant, first octant, first octant, first octant? No. So I didn't give you any restrictions. Theta goes from 0 to 2 pi. Good? Oh, at the bottom of the page, does it say some known cones? Yes.
Yeah.
Cones you need to know. Phi equals pi over 6 is better known as the cone z equals square root of 3x squared plus 3y squared. Or you might see it as, I'm not going to square it. You might see z squared equals 3x squared plus 3y squared. You might even see the square root of 3 factored out, okay? I know this stuff's kind of boring a little bit, especially, well, the Jacobians will be a little boring. But the last exam is actually a lot more fun, for me at least. I'll try and make it as fun as possible, but fuck it. Like, when you get to the last part, the death throes of Calc 3, it's so fucking cool. So I think you guys will like it, I'll try and make it fun. Cool? Alright. Good. Those are your known cones.
Let's just memorize those.
Memorize them. If you want to, you can have the general formula for a cone. Phi equals A corresponds to Z equals arc tan 1 over A times square root of x squared plus y squared. Arc tan of A. Oh, fuck. Oh, shit. Whoops. Tangent A. Tangent 1 over A. Nope, that makes no damn sense.
So don't worry about that.
Don't worry about that. I'm sure you can convert from square root of a squared x squared plus ay squared to you just like an arctangent of 1 over a. Don't worry about that. The one you need to know anyways. Problem 19. Evaluate the triple integral of 1 over square root of x squared plus y squared plus z squared where e is the solid above z equals 2 and inside x squared plus y squared plus z squared equals 4z. Alright, you're going to hate me for this one. I'm going to try not to draw it, but then the drawing would help. First things first, though, is convert the integral with triple integral of 1 over the square root of x squared plus y squared plus z squared is better known as 1 over what? 1 over rows. And then your conversion from Cartesian to spherical is rho squared sine phi d rho d phi theta. Phi theta. So the triple integral of rho sine phi d rho d phi d theta. Okay. Bounds on rho a little bit hard. It says above z equals 2, right? Z equals 2 is what shape, by the way? Here we go. Planes, just like z equals 0 is the xy plane, z equals 2, that's the 2 floors up, right? And then x squared plus y squared plus z squared equals 4z is also, it's not a plane, but it's what shape? It's a sphere, but it's been shifted up. If you complete the square, you'll find that it's a sphere rather, centered top. It's x squared plus y squared plus z minus 2 squared equals 4. You can complete the square on your own to show that, but that's the equation of the sphere if you rewrite it using in standard form. It's a sphere of radius 2 centered at 0, 0, 2. Think of a basketball sitting on top of the gym floor. Yeah.
Would you ever calculate rho given those, like the x squared plus y squared c minus 2? Because if there was no minus 2, then you would have rho equals 2.
Yes, this is let's. I hope this answers your question. We're going to want to figure out what the equation of this ball is in a second by starting back where we started. X squared plus y squared plus z squared equals what? 4z. Let's convert this to spherical. We're going to want to do that now. What is this?
Rho equals 4 minus 4.
Rho squared equals what's 4z?
4z.
4 what? 4 is
Sine.
rho cosine phi.
Yeah.
So rho squared and 4z is rho cosine phi. So we have 4 rho cosine phi. I'm going to divide both sides by rho, so this is rho equals 4 cosine phi. That's the equation of that ball. Don't forget that there's also a plane involved here, namely the plane z equals 2. Now because the sphere is centered at x equals z, or at 0, 0, 2, the plane kind of divides this in half. Does that make sense? Kind of cutting the ball into 2 equal halves. This is z equals 2. So here's what we're looking at here. We're looking at this yarmulke. That's not quite a yarmulke. Too domish. Cool? So it's this dome up here. As I draw a ray out from the origin, what do I hit first? I hit that plane. Remember there's a plane there. I don't want you to think it's an open bottom, but it's hit the plane first. What's the equation of the plane?
2.
Z equals 2, right? But that's a problem because our bounds are in terms of what? Rho. Z equals 2. How can I put that in terms of spherical coordinates? Z equals what? Rho cosine phi equals 2. Solve for rho there. What do I get? Rho equals 2 over cosine, better known as secant phi. So that's your lower bound. Pretty cool. And I believe if you flip back a few pages, if you would, to my chart of graphs. Nope, I didn't put plane on there. Never mind. Never mind. Anyway, 2 secant phi. That's your lower bound. What do I hit as I leave the region? What shape do I hit? The sphere, the upper half of that sphere, whose equation was what? Not spherical. 4 cosine phi. That's your upper bound. Those are hard to do because anytime the sphere is not centered at the origin, anytime the circle is not centered at the origin, you have to kind of shift and tweak it. So you would x squared plus y squared plus z squared equals 4z. You replace that with rho squared. You replace that with what you know it to be in spherical coordinates, 4 rho cosine phi. So you replace those by those things that you know in spherical coordinates and convert that to a nice spherical equation. Good. So that's a good. That's your upper bound. How do we do it again? Z equals 2. I said, how the fuck do I convert that to spherical? Well, z is equal to rho cosine phi. Solve for rho and you get rho 2 secant phi. Good. How about my bounds on phi? This is kind of hard. This distance will be 2. This distance will be 2. Oops, shit. That distance. This distance is 2. That distance is 2. So what kind of triangle is this? It's a right triangle. It's also got something with an eye. Isosceles. It's an isosceles right triangle, which tells you that any of the lesser angles are what measurement? 45 degrees, better known as in radians. Pi over 4. So, but again, we want to be inside this cone, or inside this sphere. So straight up would be what? This straight up corresponds to phi equals what? 0. And we blossom outward to pi over 4. So 0 to pi over 4, my bounds for phi. And then lastly, when I bound on theta, I don't seem to restrict you based on any quadrant, right? No octant like that. So 0 to 2 pi.
Is there any other way to figure out that that's pi over 4?
Nope. Yeah, kind of tough.
Can you explain how you got pi over 4 again?
Sure. The radius of this sphere is what radius? 2. How high are you up the ground here? 2. This is an isosceles right triangle.
Right.
2, right angle. If you have an isosceles right triangle, all you know from geometry is that the sides opposite the angles are equal. So if you have 90 degrees used up and 180 degrees in any given triangle, so therefore 90 degrees left up to split between 2 equal angles, you have 45 per, right? Got it, cool. Flip back to the previous page if you would. It was what? Rho to the fourth cosine. So I set up the integral. There's a lot of work here. I didn't want to do it, and besides, we're running in 38 minutes. Shit, I would love to get one of these practice tests. Oh well. This integration is really hard to do. Notice that there's a rho to the fourth. So this is flipping back to the previous page for a second, if you would. I'm going to notice that the bounds on all these integrals are constant. So I can split this up into 0 to 4, rho to the fourth d rho, times integral from 0 to pi over 6 sine cubed phi d phi, and integral from what, 0 to pi? Of sine theta cosine theta d theta. This one, not bad, it's rho to the fifth over 5 from 0 to 4. Cool. This one, not that bad, you do a u sub, you could say that's u, so guess what, that's du. Happy day. So our sine squared theta over 2, 0 to 2 pi. This guy, pain in the ass. But flip back to the previous page. Another page. I gave you another page. I gave you some integrals back in the polar coordinate section. Here they are. If you look on page 5, I gave you a bunch of integrals. Sine cubed and cosine cubed tend to come up every now and then. So it might be worth your time to memorize those integrals at the bottom. And by the way, you're probably going to need to invoke the integral of cosine squared and sine squared on the bottom as well. Those are the half-angle formulas that you used in Calc 2. You probably forgot them, so I provided them to you at the bottom of page 5. So look at that page and even consider memorizing the sine cubed and cosine cubed ones because those might show up in a problem like this. Okay. We're not going to do number 20. Just going to skip that, do it on your own, something all the time. Area and volume. This is worth discussing a little bit. So what does a single integral give you? Area. Unless you happen to do the double integral of 1. This also gives you area. This confuses people because I told you earlier that a double integral gives you what? Volume, right? So why does the double integral give you area? If I do the double integral of 1, I actually get the area, and here's why. What does it say about the surface? This is z equals 1. So here's what the shape would look like. It's just black. Let's just say the region D is this shape here, some jelly bean shape. Okay, not so much jelly bean anymore. And the height is what? 1. Now, what's the volume of the green shape, the giant shape altogether? The volume would be whatever the area of the red shape is. Area of the red guy times what? Times the height. But what's the height? The height was 1. So what is it essentially saying? The area of the red guy is equal to what? The volume, which we're technically finding by computing this double integral, right? So what is this really saying? The double integral does always technically give you a volume, but it turns out the numerical value of the volume happens to be the volume or the value of the what? The area. That's all that's happening here. Cool. So if they ask you to find an area of a shape, do a double integral of 1 dA. Cool. As in the next problem we're about to do, it says find the area between what? Oh, some polar curves. Yay. 5 cosine theta, but outside 2 plus cosine theta. This is again where you might want to go revisit some polar coordinate graphs. So 5 cosine theta looks like this. 2 cosine theta looks like this. 2 plus cosine theta. So inside one, but outside the other, right? I want this loon here. It's called a loon. All right. L-U-N-E, loon. How would I find the area? Well, you remember a formula. Do you remember the formula last year? It was integral of what? 1/2 r squared of theta d theta. You guys remember that? 1/2 r squared d theta. So who remembers that formula? 1/2 r squared. Find the area of a polar curve. No one remembers that. What do I write it again? That's the formula that you use to find the area of a polar curve. Back then. And because this actually had 2, you had to do. This was exam 3 stuff, right? From Calc 2. You did outer minus inner. Bigger radius, big radius, minus small radius. And those are your bounds. But now, we're doing a double integral. We're doing the double integral of 1. What's our polar coordinate conversion? R dr d theta. What are my bounds on R? Well, as I draw a ray out from the origin, what do I hit first? Do I hit the jelly bean, the cardioid, or the mission, or the circle? The mission, which has equation 2 plus sine theta. 2 plus cosine theta? Are you expecting me to laugh? No.
The croissant.
You did do the bad guy.
Bad
Oh,
minute.
okay.
5 cosine theta.
You heard the no.
And then, what about my bounds on theta? That's a bit harder. I'm going to set these two equal to each other. Remember, setting 2 plus cosine theta equal to 5 cosine theta to figure out what values of theta cause the intersection? That would be cosine theta equals 1/2. What is cosine theta equal to 1/2? That would be for pi over 3 and negative pi over 3. So there's a set of your integral. But I wanted to point this out, by the way. When you do this integration, here's what you get. You get r squared over 2. Hey, what is that? That's the formula that you learned in Calc 2. When you integrate r, you already did it, you get r squared over 2. Plugging your upper bound, plugging your lower bound, you get 25 cosine squared theta over 2 minus. You guys probably remember doing these now that you're watching me write this out. Thinking, oh my god, I remember integrating these horrible, horrible things. Integrate from negative pi over 3 to pi over 3. And when you do that, you get an answer. Sorry, my shoulder's in the way. Cool? Where is that laughter? It's on the other side of this wall. Guess so.
2.
Alright, it must be the same way that the double integral of 1 dA is the area of D. It's also true that the triple integral of 1 dV is the volume of E. So you can do that to problem 22. I'm not going to talk too much more about that one though. Stop start. What are we doing on time? Jacobians. Then we got Laplace transform, or not Laplace transform, sorry. Lagrange multipliers. Okay. These are kind of hard. The Jacobian of a transformation is just, you'll see me doing this problem 23. Use an appropriate substitution to transform the integral x over y squared. dA. Okay? And I say that the region of integration is xy equals 1, xy equals 3, y equals x squared, and y equals 2x squared. What you'll tend to want to do is divide both sides by, or get everything over so you have some function of x and y equals number, which is like this. Some function of x and y equals a number. Some function of x and y equals a number. That's not quite true here. We have a function of y and a function of x. So what we're going to do is we're going to divide both sides by x squared. Cool? Now when you see this, these substitutions are screaming, they're screaming at you to make this sort of substitution. Namely, that you should say, we're going to say u equals xy, and v equals y over x squared. Does everyone see that u equals this guy and v equals this guy makes a good substitution? And by the way, what will our bounds on u be? 1 to 3. What will our bounds on v be? 1 and 2. Makes it really nice, right? We'll get there in a second, though. We have to compute the Jacobian. The Jacobian works like this. Now, some people do that. Here's this all the time. X and y, you know, there's x and y, or I guess for, yes, okay. X and y, right? Now, x and y, u and v. So x goes with u, y goes with v. So as long as you do partial u, partial u, partial x, and partial v, partial y in the corners, it doesn't matter how you mix and match the other ones. Does anyone know why? Because when you do a determinant, 3, 7, 1, 4, this determinant is 3 times 4, which is 12, minus 7 times 1, which is 7, which is 5, right? But what if I switch the 7 and the 1? There we go. So what's a 1 now? 3 times 4 is 12, 1 times 7 is 7, 12 minus 7 is again 5. So it doesn't matter if you flip-flop, if you say partial u, partial y, and partial v, partial x, or you can say partial u, partial y, and partial v, partial x. It doesn't matter where you put those. Cool? So everyone with me? Here's u. Take the partial derivative with respect to x. What do you get? Take the partial with respect to x. What do you get? Y. Down here, take the partial derivative of this guy with respect to y. 1 over x squared. Take the partial derivative. Now, it doesn't matter. I'm going to take the partial derivative of this guy with respect to y now. So I'll get what? x, doesn't matter where I put it, I'll put it here. And take the partial derivative of this guy with respect to x, that would be negative 2y over x cubed. Multiply the main diagonal, y times 1 over x squared, minus, multiply this main diagonal, negative 2y over x squared, because one of the x's cancels. So I end up with y minus negative 2y, or 3y over x squared. Okay, so now we're going to have double integral x over y squared. What's our Jacobian? Be very careful here. My Jacobian, look at the top, look at the middle of the page, or the middle of that paragraph. It says, oh, you got someone coming in. It says, keep in mind that if a transformation is given as u equals v equals, look up, as u equals v equals, then this determinant is not your Jacobian. Your Jacobian is the reciprocal. So your Jacobian isn't 3y over x squared. What's your Jacobian? X squared over 3y. Okay? So we're going to say x squared over 3y is our Jacobian du dv.
Now, could you repeat when that condition comes into effect?
Sure. If I have u equals v equals as my substitution, then my Jacobian needs to be reciprocalized. Not a word, but I'm using it like a word. Anyway, if I said x equals u squared minus v squared, y equals 2uv, this is a substitution wherein x equals y equals, and I don't take the reciprocal of my Jacobian, that determinant to get my Jacobian.
Oh, so if we have to like figure it out, then it's gonna be this.
You don't actually have to solve for u or v though. You can start. You can do your Jacobian from here. You can do partial this guy with respect to u.
No. What I'm saying is just that if we get like a set of conditions.
Yeah. Looking like this and
like,
solve. Yes. Right. Yeah. That's a good reason. That's a good way of putting it. Yes. Okay. So we have x over. So let's how does this simplify here? We have the double integral of x cubed over 3y squared du dv. Now this is 3y cubed du dv. This is kind of a pain in the ass because now we have to figure out in what kind of combination can I cause these x squareds and y squareds to become u and v's. We happen to know that v is equal to y squared over y over x squared, right? So let's write this down. V equals y over x squared. So what's 1 over v? Well, that would be x squared over y. Anyone agree to that? So I'm going to use up 2 of the x's and 1 of the y's to give myself a v. It was formerly x cubed over y cubed, but I used up 1 of the x's, 2 of the x's in the numerator and 1 of the y's in the denominator to replace that with a 1 over v. Cool? I'm going to do it again. I'm going to use up 1 of the y's in the denominator. I'm going to use up 2 of the x's in the numerator. Well, how many x's do I have up there? I only have 1 x up there. So I use up 1 up top and put 1 on the bottom. If I had 1 x on the top but I need to use up 2, that means I took away 1 from the numerator and put 1 in the denominator. So I'm really using up 2. What is y times x in terms of the substitution we've used? U. So I can replace x times y by u. And now my integral is all in terms of u and v. 3uv squared. Alright? What are my bounds on u? Here was u. U was equal to 1, u was equal to 3. My bounds on u go from 1 to 3. My bounds on v go from where to where? 1 to 2. So when you do this integration, you get 1/3 ln of 3 1/6 ln of 3. That should be the result of your answer. I think it should be your answer. 1/6 ln of 3 when you do that integration out. Good? And let me know if you have any problems with that. Alright, next one. We're going to do a couple more and then run multipliers. I don't think we'll have time to get to a test unless it happens to be the case that this room is vacant for the next 2 hours. We'll have to check with the front desk if you guys want to do a practice test. Otherwise, we'll just call it a day and go home. Okay. What's the next one? Use an appropriate substitution to transform the double integral of 2y minus 2x over x plus y, dA, where d is the region bounded by the curve. So once again, they kind of just give us these curves. What, x plus y, x minus y?
X minus y equals 1.
Yeah.
X minus y equals 3. X plus y equals 1. And x plus y equals 4.
So once again, I'm going to say u equals x minus y and v equals x plus y. So let's get our Jacobian really quick. So you missed it, Mark's bar. When I take the partial derivative of u with respect to x, what do I get? 1. x and u go together, y and v go together, right? That's 1. What happens when I take the derivative of v with respect to y? 1. At this point, it doesn't matter, and this is what you missed, it doesn't matter where I put the other ones. When I take the partial of u with respect to y, what do I get? Get -1. I'll put it there. But I could have put it over here. Keep that in mind. I could have put it there. Partial derivative of this guy with respect to v, or partial derivative of this guy with respect to x, I get 1. 1 times 1 is 1, minus -1 times 1 is -1, so I get 2. So what's my Jacobian? 1/2. Why is my Jacobian 1/2? Because when you say u equals v equals is your substitution, this is a crucial thing. This is u equals v equals. You need to say 1 over that determinant is your Jacobian. Cool? So, double integral 1/2 du dv. Oh, by the way, you always take an absolute value of Jacobian. The reason this is the case is because if I believe that, and this is pretty sure I'm right about this, if I had chosen this to be v and chosen this to be u, the result of my Jacobian would have been -2, or my determinant would have been -2, so I would have got a -1/2. But you don't want that negative to fuck up the integral, so it's always the absolute value. I think he did this once, like 2 semesters ago, where he didn't put absolute value, like he said, the conversion is, in fact, if you go on the previous page, I hope I put absolute value. Did I? Yes, in the upper right hand corner, absolute value j du dv. He did this once, dx dy equals j du dv, and I think it was false, because there's no absolute value.
Is it going to be bolded on the exam?
No, the bold's not relevant. I don't know why I meant that bold.
I was just wondering.
Not a vector. It's definitely not a vector. No, don't worry about any of that shit. Okay, and then what's 2y minus 2x? What is that in terms of u and v?
2u.
Not quite. Negative 2u. Then x plus y to the bottom, that's a v, right? My bounds on u go from 1 to 3. My bounds on v go from 1 to 4. Negative u over v, du dv. This gives me negative u squared over 2. 3 squared is 9, minus 1 is 4. There's 8 over 2 is 4. Negative 4 over v. This is really weird. No, I guess it's right. I guess it's fine. I think you need to write that. I think it's negative 4 down to 4. I think that should be your answer when you do this iteration. Yeah.
Where are you getting these U's and V's?
What? Oh, sorry. What is u? U is equal to what? X minus y. Anytime you have a function of u and v on the left-hand side, you might be enough for this. When I have a function of u and v, or when I have a function of x and y on the left equaling some number, that's a good choice for you. In the previous problem, we had x, y equals 1 and x, y equals 3. That's screaming, hey, make me u. Okay? And then if I had a y equals x squared, and I also had y equals 2x squared, I don't have a function of x and y equaling a number, so I divide both sides by x squared. And now I have y over x squared equals 1, y over x squared equals 2. That's v. Cool? So whatever you have on the left-hand side of which equals a number, that's your choice for u and v. Stop, start. Okay, next one. This is a good one. Find the volume enclosed by the planes x plus blah, blah, blah. Okay, here's what we're going to do. How do I find the volume? There's 2 ways to find the volume. I can do a double integral, which I'm not going to do here, or I can do a triple integral of what? 1. I'm going to do the triple integral of 1. I don't know if you guys are out of the room for this, but you can do the triple integral of 1 dv if you want to find the volume of a region. So we're going to do a triple integral of 1. And the bounds are these crazy planes, right? X plus 2y equals 1, x plus 2y equals 3. Huh, I see the same thing repeated twice. We better make u equal, what was it, x plus 2y?
Yeah.
What's v? Y minus 3x or 3, y minus z? And what's w?
3z plus x.
3z plus x? Cool. So let's go find our Jacobian. This is going to be a 3 by 3 matrix though. What's the partial derivative of this guy with respect to x? 1 with respect to y. 2 with respect to z. 0. Next row, we're going to take the partial derivative of v with respect to x, y, then z. What's the partial derivative of y minus z with respect to x? 0 with respect to y. With respect to z? -1. How about the partial derivative of w with respect to x? With respect to y? With respect to z? 3. Take this determinant. I know it's been a lot of people looking at. It's funny because you did like a cross product like in August, and then when I take this determinant, you're like, what the fuck are you doing? Like a cross product. Just instead of ijk, you have 1, 2, 0. So here's your determinant. 3 -1 minus -1, but -2. Oh, my fucking boring. Fuck. Oh well. I want to be a different number to show you, hey look, is that your Jacobian? Technically yes, because the reciprocal of 1 is 1. But if it had been 7, let's just pretend right now for a moment that 3 minus 2 is 7, what's your Jacobian? 1 7, because I have u equals v equals w equals. Cool?
So it's reciprocal, but then it's also an absolute value.
Yes.
Reciprocals make negative, right? And then
Your power is negative. No, not negative reciprocal. I'm not talking about perpendicular lines. You're thinking negative reciprocals because you want perpendicular lines. Just reciprocal just means 1 over. So you get 1. What's your Jacobian then? It's 1 over 1, which is fucking 1. Okay, great. So we have double triple integral of 1, let's say du, dv, dw. What are my bounds on u? Remember, u was equal to x plus 2y. What were the planes x plus 2y bounded by? X plus 2y equals 1 and 3. And then how about for y minus z? What were those planes? Y minus z equals what and what? 2 and 5? Well, and this interval comes out to be 2 times 2 times 3 is 12. Good. So the volume of that region is 12. I think that's it. Now we're moving on into Laplace. I keep saying when I say Laplace transform. I mean Lagrange multipliers. Laplace transform is a different class. All right. This is the last section, and we've got 15 minutes to do it, so this will be a piece of cake. Here's what we're going to do. Oh, shit, man. All right. Second. Talk amongst yourselves. Help me tell a joke. Here's a good joke. All right, ready? 2 jokes. One's dirty, one's not. So there's a zoo. Mind if I use this? Thanks. He didn't even say yes. All right. There's a zoo, and it's got a really famous gorilla exhibit, and the gorilla dies. And the owner of the zoo, it was a really popular exhibit. The owner says, listen, Mike, we're going to have you dress up in a gorilla suit. I'll pay you like double for the week. But until we get a new gorilla, and I just need you to dress up in a gorilla suit and go in the cage and pretend to be a gorilla. And he did that. Was pretending to be a gorilla, and a lot more people came than ever. It was great. It was amazing. People were like, wow, this is a really lifelike gorilla. He's like doing all these crazy tricks. And the last day, he climbed the fence and climbed over the top and tried to showboat, and he fell into the lion's den. And he was like, oh shit, I'm in some trouble. So a lion pounces on him and says, help, help! And the lion says, shut the fuck up, you're going to get us both fired. All right, one more joke. Guy walks into a bar and orders 10 shots of whiskey. 10 shots. Yeah, and bartenders give him the first shot, pouring the other, and I say, wow, what's the occasion, man? And the guy says, first blowjob. And the bartender's like, really? You're going to celebrate that much? And the guy's like, I'm trying to get a taste in my mouth.
Oh.
Okay. All right. Lagrange multipliers. Determine the absolute extrema of f of x comma y. This looks like absolute extrema, like an enclosed region, but it's subject to a curve. So you have a primary and a constraint. Your primary is 2x cubed, 2x squared plus 3y squared plus 4x minus 1, and your constraint is x squared plus y squared equals 9. So this is your g, and this is your f. Here's what needs to happen. You need to set fx equal to lambda gx, and fy equal to lambda gy, and fz equal to lambda gz if needed. So let's do this now. What is partial derivative of this guy with respect to x? Good job. Ready to take it? 4x plus 4 equals lambda times what? What's the partial derivative of this guy with respect to x?
2x.
I get this question a lot. Andrew, do I have to subtract the 9 over? Well, what's the partial derivative of the 9 with respect to any variable? 0. So who gives a fuck if you put the 9 here or on the other side? Doesn't matter, right? It's just a constant. So ignore that. Over here, partial derivative of this guy with respect to y, that would be 6y equals lambda times partial derivative of this guy would be 2y. All right. Now I'm going to ask you to solve one of those equations. Actually, let's put it this way. How many equations do I have? 2. How many variables do I have? 3. X, y, and lambda. That's a problem. We have 3 variables but 2 equations. What's our third equation? Or what's our leftover equation always?
Constraint.
It's always your constraint. X squared plus y squared equals 9 is the third equation you're going to work with, and we're going to reference that when we need to. But we're going to start with these first. Which equation would you like to solve first? The first or the second? Second looks a bit easy. Be careful here. You're going to make a mistake that I don't want you to make. What looks like something you can divide through by? y. And if you do that, you get lambda equals 3, which is fine, but you lose a solution. What solution do you lose?
0.
Y equals 0. You should subtract lambda 2y over to get 6y minus 2y lambda equals 0. Then factor out the 2y. And when you do so, you get 2y times 3 minus lambda. So you have two possibilities. You either have this timeline wherein y equals 0, or you have a timeline wherein lambda equals 3. It's like a Back to the Future thing. You've got this timeline versus this timeline here. We have to go back and stop Biff or some shit. Okay. You want to see Back to the Future? One person, good. Okay. Y equals 0, lambda equals 3. Let's start with the y equals 0 case. Well, we don't actually have to come over here. That's nice about this. Is that if y equals 0, come straight here. If y equals 0, what possibilities do we have for x? X is equal to what?
3.
Plus or minus 3. So you have 3, 0, and negative 3, 0. But the lambda equals 3 case can't be resolved over here in your constraints. We're going to have to take lambda equals 3 and throw them over here. 4x plus 4 equals 3 times 2x. 4x plus 4 equals 6x means 4 equals 2x. Wow. Means x equals 2. And if x equals 2, that leads to some possibilities. We have either 2 comma, 2 squared is 4, subtract from 9 gives you 5, so you have either root 5 or negative root 5. So those are your 4 critical points. You're going to plug them into your original equation. Whichever is your largest value is your max, whichever one is your smallest is your min. That's that simple. Cool? Would anyone like me to plug these in? Sure, why not? If I plug in 3, I get 3 squared is 9 times 2 is 18, 3 times 4 is 12, so I get 30. Oh, minus 1. 29. Same thing when I plug in, oh no, it's not quite when I plug in negative 3. Negative 3 squared is 9 times 2 is 18, minus 12 is 6, minus 1 is 5. So 29, 5. I'm going to put this over here. 29, 5 here. 2 comma root 5. Fuck me, right? 2 squared is 4 times 2 is 8. Root 5 squared is 5 times 3 is 15. Plus 2 times 4 is 8 minus 1. That would be 30. Same thing when I plug in the other guy. So what's your absolute max?
3.
What's your absolute min?
5.
That's it. Cool. One more, and then we're going to stop. And we have 10 minutes after that, which you can ask questions. I guess there's no time to get to a practice exam, but if you have questions about the practice exam, please ask. I'll put answers on the group page. And I'll stop the video, say some last things. Okay. In order to create your best imitation of a Chipotle burrito, you have $60 to spend on guacamole, G, which costs $10 for each tablespoon you use. We all know how expensive that shit is. And cheese, C, which is $2 for each handful you use. It is determined that the quality of this burrito is given by the formula 4GC plus 3G minus C squared over 2. There's no actual empirical evidence to suggest that the quality of a burrito decreases by the square every handful of cheese you put on it. That doesn't even make sense to me. I feel like more cheese is better, but whatever. It is determined what combination of ingredients make the best burrito. Remember, you have a limited amount of money. You have $60, and each tablespoon of whatever of guacamole is $10, and each handful of cheese is $2. So this is your constraint. This is your primary. Ready? Set? Go. I'm going to say fx, or we're going to say fg, I guess, equals lambda gg. Good game. And fc equals lambda gc. And then we have our constraint 60 plus 10g plus 2c, or better known as 30 equals 5g plus c. Good. All right, now, take the partial derivative of this guy with respect to g. We get 4c plus 3 needs to equal lambda times 5 lambda. And then we're going to take the partial derivative of this guy with respect to c, and we get 4g minus c, and this equals us. Oops, you know what? I made a mistake. Careful. Don't divide by 2 yet. This is your constraint. This truly is your constraint. So this should be 10 lambda, and this should be 2 lambda. That will mess things up slightly. Maybe they won't actually. All right. Cool. Now, and then lastly, our constraint to this guy, which now we can go ahead and use the simplified equation because now we're just solving a system of equations and we can divide 3 by 2, whatever we want to. All right, here's what I'm going to do. 4c plus 3 is equal to 10 lambda, and 4g minus c is equal to 2 lambda. Well, this would be 5 times this guy, right? Can we get 10? Wow, I'm glad I caught that. So this guy is 10 lambda, this is 2 lambda. This equation is 5 times this guy, so I'm going to put 4c plus 3 equals 5 times this guy. So 20g minus 5c. This looks horribly wrong. I don't know how to do it. This seems weird. Oh well. It works. So 20g minus 9c needs to equal 3, and we have 5g plus c equals 30. I'm going to multiply it depends on what you like. It's up to you. If you like to use elimination or substitution, I like elimination. So I'm going to do minus 4 times this guy, which means I'll get 0g. Oh, these will cross. 0g, like no gravity. Minus 13c. 3 minus 120, or sorry, 3 minus 120 is negative 117. Oh, that works out really well because how many times does 13 go in 117? 9. Now, if you use 9 handfuls of cheese, that means you're using up some amount of money, but you can basically solve for g here. 9 subtracted from 30 gives me 21 equals 5g, which means you're using 4.2 teaspoons or tablespoons of guacamole. So the optimal combination is 4.2 equals g, and c equals 9. You have to be very careful, though. I'll only give you one critical point. So this critical point could very well cause a what? Well, we're trying to make the best burrito, right? We want quality to be maximized. Well, since we only have one critical point, it could very well be the case that this combination causes what? The minimum, right? We don't know for a fact that this is the maximum. So what we're going to do is we're going to figure out the associated quality of this burrito. Fuck, I have to plug this in. 4.2 times 4 times 9 would be 37.8 times 4. What's that? 37.8 times 4. 38 times 4 is 76. 140, 150. Let's say 150. Sure, great. Plus 3 times u, so plus 12-ish. Minus 9 squared is 81 over 2 minus 40. So 110 plus 12 is 122. It's a good. I don't know what we're measuring our quality in. I don't know how happy we are when it comes back out of us. And then we're gonna use it up. So here's the other thing. We need to use a point on the constraint. You can't just say, well, what if I put a shit ton of guacamole on it and a shit ton of cheese on it? Is that gonna get a big number or a small number? We have to use something that's subject to the constraint. So pick a nice combination that will work. You can do something like g equals 3. Wow, g equals 3 and c equals 15. Right? That would work. 3 times 10 is 30. 15 times 2 is 30. 30 plus 30 is 60. Well, what will this combination do to us? What kind of burrito will we get? We'll get 4 times 3 times 15 plus 3 times 3 minus 15 squared is 225 over 2. So we have 4 times 3 is 12 times 15 is what? 6 times 30 is 180 plus 9 minus 225 over 2 is about 110. So we get 180 minus 110 is 70 plus 9, 79 quality burrito versus a 122 quality burrito. So this is indeed a maximum. Cool, thank you, good night. So, there's 5 minutes left. If you want to talk about the practice problems, we can talk about that, but it seems like you guys are all happy.
Could you use 6 tablespoons of guac and then set C equals 0?